All right, I'll wait a second for everyone to join. All right, good evening, and thank you all for joining us. We'll get started in just a few moments, and as we wait for the attendees to join the event, and while we wait, let's get an idea of where the audience stands regarding radiological risk. So we're going to launch a survey question right now, and that question is, do you think radiological risk can be managed? So please vote on Zoom, answer that question. All right. Do we have the result of that poll as folks are still joining? All right. It looks like 82% strongly agree that radiological risk can be managed. 17% somewhat agree. So I think maybe we're preaching to the choir today, but I think this will be a really informative webinar to discuss how and why radiological risk can be managed. So with that, hello and welcome to Radiological Risk in Perspective, presented by the American Nuclear Society. This evening's webinar is part of our Educator training program, which is specifically developed for elementary through high school educators. My name is Chris Perfetti. I'm an associate professor of nuclear engineering at the University of New Mexico. I was the presenter for the last one of these webinars, so I really enjoyed that experience and really enjoyed you all joining, and hope you all also enjoy this one too. And before I sorry, my email sounds are still on. Before I introduce our presenter, I'd like to cover a couple of quick notes and logistics before we start the event. So if you have any questions, please type them into the Q&A feature on Zoom. We will attempt to address as many questions as possible at the conclusion of this talk. This event will be recorded for everyone, and a link to the recording will also be provided to you via email, so to all registered attendees. So feel free to watch this event later on. All right, and certificates for attendance for today's webinar are available on request. So please email us at askanything@ans.org to request a certificate. And that email address is being dropped into the chat momentarily. This is a very handy email address. It'll come up a couple more times in the next minute. So next, if you would like to learn more about ANS nuclear education events, programs, and resources, you can always visit our website at ans.org/nuclear, or you can email our senior manager of STEM programs for the American Nuclear Society, who is Uchenna Izibe, at uezibe, that's UEZIBE, at ans.org. And Uchenna is also dropping his email address into the chat as well. Now, for educators in the audience, please do let us know if you'd like an ANS member to visit your classroom, either virtually or in real life. You can feel free to request this at askanything@ans.org. Another point to note, so for ANS members, one of the perks that we have is that we have a new Nuclear Ambassadors program, which offers members free training in K through 12 education outreach. So please contact Uchenna if you are interested in training for your organization. Finally, we'd ask that all participants adhere to the ANS Code of Ethics and Respectful Behavior Policy, which can be found at ans.org and is being dropped into the chat. So with those notes out of the way, I'd like to introduce today's presenter. Dr. Robert Hayes is an associate professor of nuclear engineering at North Carolina State University, and he is a joint faculty member at Savannah River National Laboratory. He is a licensed professional engineer, certified health physicist, and a fellow of both the Health Physics Society and the American Physical Society. His research focuses on radiological risk assessment, radiation shielding, nuclear forensics, nonproliferation monitoring, retrospective dosimetry, air monitoring, and nuclear waste management. He previously held senior technical roles at the Waste Isolation Pilot Plant and the former Nevada Test Site, supporting operational radiation protection and safety analysis. Dr. Hayes also serves on the U.S. Department of Energy's Advisory Committee on Nuclear Security, contributing to national guidance on radiological safety and risk communication. His work integrates experimental measurements, regulatory compliance, engineering modeling, and public engagement to advance radiological protection in both technical and societal contexts. He is also a famous TikTok influencer extraordinaire. So I strongly suggest that you look him up on that platform if you use it. And with that, I'd like to welcome Dr. Hayes.
Hey, everybody. You see the slides good? Hear me? Fine?
The slides look good.
Okay. And now let's make sure they advance. Did it advance? We're good?
You're good.
All right. Here's what we're talking about. First, I'm going to go through the fission fuel cycle to basically let people understand where does radioactivity come from when we're making electricity and how does that go through the process. And then we're going to contextualize radiological risk. What is the risk? 10 to the minus 5 joules per kilogram. What is that? What's a millirem? I mean, who knows, right? Those are gobbledygook numbers. Let's contextualize that. And then we're going to have a little bit of a focus on nuclear waste. And we're going to talk about environmental impact. What is the radiological risk versus the environmental impact? And then probably what's on a lot of people's mind are the nuclear accidents. And let's contextualize the radiological risk of those nuclear accidents. So start off with, let's talk about fission. So when you do fission, as you can see here, as you can see here in the top left, a typical fission will give off about 200 mega electron volts of energy when a uranium-235 nucleus fissions. Now, if I'm combusting fossil fuels, you only get about 1 electron volt per atom in that reaction that you see down here. Now, what we see here on the upper left is that barium and krypton are being made, but in the top right, in the top right, you can see that there are a lot of different types of fission products that can be generated. And in this middle graph, you see a histogram of the different distributions that you can get from a typical uranium-235 fission. So you get a lot of different isotopes, different elements with different amounts of neutrons giving different isotopes, and a lot of them are radioactive. And so that's going to be an important point to contextualize what we'll be talking about later. So now let's talk about the fuel cycle. So historically, you go and you dig a hole and you dig up some dirt that's got a little bit more uranium in it. It might only have a very fraction of a percent, maybe a tenth of a percent of U3O8. That would be the natural chemical form for the uranium as it's in the dirt. But then you have to mine it and mill it, just like with any metal or any material that you're getting out. You mill it and then you process it. And in the sequence of processing it, eventually we turn it into uranium hexafluoride, UF6. That allows us to do enrichment based on differential diffusion with the isotopes. The fissile isotope has a lower mass, and so it diffuses at a different rate than the non-fissile uranium-238. And that allows us to turn the uranium from only about 0.7% of the fissile component up to around, say, 5% of the fissile component. Once that happens, then it goes into fuel. Then we'll convert it into uranium dioxide, UO2. It becomes fuel. Then once it's fuel, it can go to the nuclear power plant where it will then make electricity. And right now it goes into interim storage. And tentatively, it could just then go straight to a deep geological repository. Now, every nuclear engineer that I've ever met, we would like to recycle it. And that would require a processing facility, which we don't have in the commercial space right now. But that's the process for making electricity. And the radioactivity comes in the uranium, the mill tailings, the depleted uranium, and then the fission products, and then trace radioactivity that comes from other things like PPE in the fuel cycle. So let's now talk about radiological risk. We're going to start with a millirem. Now, I had asked that before. 10 to the minus 5 joules per kilogram of gamma ray dose, that's a millirem. What is it? That's about what you get in a day if you're an average American. If you're an average American, you get about a millirem per day. just because you're breathing and you're walking. The Earth is irradiating you. There's radon in the air, radiation from outer space. That's going to be an important point. Now, we're going to go through a logarithmic scale to talk about radiological risk. And I'm picking 1 milligram. I could have went a lot smaller. I could have went a lot bigger. But this is going to come back later in the presentation because that's a very important point. What is your daily background? It's about 1 milligram if you're a US citizen. All right, 5 milligram. That's about the dose that you get if you take a trip from LA to New York and back. That's also the regulatory limit for drinking water. So if I have a source of drinking water that's got, say, natural radium and its decay products in it, the maximum amount of radium that you can have in that water cannot give you more than 5 milligram per year. That's about, again, the coast to coast trips. That's a really small dose. It's just 5 times your daily dose, but that's what you can get in a year with the EPA drinking water standard. And now you can start to contextualize it. How scared would you be if you knew your water violated the EPA drinking water standard? It means that it's violated the 5 rem. The question is, how bad did it violate it if you wanted to really contextualize it? 10 milligram, as Chris said, I used to work at WIPP, and any EPA regulated facility, it's got a limit of 10 milligram per year for an offsite dose limit to the nearest member of the public. Now, 10 milligram, again, that's an order of magnitude more than 1 milligram. That's about the minimum dose that you have to get just because you've got potassium in your body. Now, every cell has to have more potassium in the cell than in the fluid outside. You need more sodium outside the cell and more potassium inside the cell. And because you've got potassium inside your body, that gives you a radiation dose because potassium, like uranium, is naturally radioactive. It's only a trace amount, but it still gives you a dose. And the minimum dose you can get if you're a child or a small petite female is you're going to get about 10 milligram per year of this internal dose just to stay alive because you have to have potassium to stay alive. 40 milligram. Again, we're going to be going logarithmic doses here. 40 milligram, that's about the maximum dose. So if you're a large muscular male, you'll get around 40 milligram per year of dose just because of natural potassium in your blood. And again, the cells need to have more potassium in them than there is outside of them. So the amount of potassium in your body scales with muscle mass. The more muscle you have, the more potassium you have, the bigger your dose is going to get. Let's keep going up, orders of magnitude here. 100 milligram. 100 milligram, that's about the dose you get from a pelvic x-ray. So if you've ever had to have a pelvic x-ray, something happened to your hip, you're going to have a dose like this just in one x-ray. That's the limit to a member of the public from a nuclear facility. So if you see on the bottom right, if you can see the fence there, if I was a cowboy and I decided I wanted to go and live on that fence, then by law, I cannot get more than 100 milligram per year at the fence. That's the maximum amount at the fence that a person can get, that a member of the public can get year round. So if I was living there, that's the maximum that I could get. Otherwise, I'm breaking the law. I'm violating the license and the regulation for what kind of radiation dose a person can get at the closest uncontrolled space to that facility. Let's keep going up. 310, another order of magnitude. That's about the average annual dose that you get if you're a US citizen. And this is just based on population and where you live. But that's why 1 milligram is about what you get in a day. Because 310 milligram, that's about the average dose for a US citizen from all natural sources. This doesn't include medical exposures. This is just natural sources. Radon in the air, uranium in the ground, cosmic rays, internal potassium. 310 milligram, that's what you're going to get. And so now you can see that all of these other regulatory limits that are above that would be very scary, they're a fraction of that. Regulatory limits tend to be a fraction of natural radiation. That's just the way that we do business. And that doesn't mean that it's scary, but it can be. And it can cause a lot of cognitive dissonance to say, you're breaking the law. And if you're breaking the law, that can't be safe. And therefore, I'm in danger. And therefore, I'm afraid. And that happens a lot when it comes to these kinds of things because it's not contextualized. Unless you understand dose and context, it can be really scary. All right, orders of magnitude. Let's keep going up. If you're old like me, you've had a stress test. If you had a stress test, you've had radioactive thallium injected into you, and they imaged your heart as your heart was pumping. That'll give you about 1,000 milligram. Similarly, if you had a CT scan to the head or to the torso or even to the hip, that's about 1,000 milligram. And from a health physicist point of view, that's perfectly fine. if you need to have a stress test, you need a stress test. If you need a CT scan, you need a CT scan, and that's perfectly fine. But here's another case where cognitive dissonance comes in. At 1,000 milliram by law, the EPA, if there's a nuclear accident, I used to work on the teams that did radiological emergency response. I was on the federal teams. If a member of the public could get 1,000 milliram in a year, the EPA could issue evacuation orders. And if it was a half a rem per year after that, or 500 milliram per year after that, they could extend those evacuation orders. Remember, natural background is 310 or 320 milliram per year, but that limit is 500. So they're extremely conservative, and people don't understand that that's the case. That 1,000 milliram is the same dose you get for standard medical procedure, but it could also trigger emergency evacuation, and that can cause cognitive dissonance. Keep going up, orders of magnitude, 5,000 milliram. That is a legal dose to a radiation worker in the United States. That's considered a safe dose. It's considered for whatever risk may be there. If there is risk at 5,000 milliram, it's small compared to, or it's tolerable compared to standard industrial risks. So if you have a job, you're accepting risk from your job, and this is considered well within the OSHA specifications. Let's keep going up, orders of magnitude. 10,000 milliram. We finally hit the point where there are quality peer-reviewed journal articles that show that children that have had radiotherapy, now at this point, they have found that you can have a statistically significant increase in cancer probability all the way up. So we're going up orders of magnitude, orders of magnitude. This is the lowest dose that any scientific research has found credible evidence that you can have a measurable increase in your cancer probability. Now, to put that in context, that 0.5%, that's about what you get, about a 0.5% increase in your cancer risk at 10,000. That's a huge dose. If you live long enough in the US, you have about a 40% chance of getting any kind of cancer, all cancers combined. If you live long enough, 40% of us are going to get cancer. And so at 10,000 milliram, that's been increased by 0.5%. So in other words, if you had 100 people and they lived long enough, 40 of them on average would get cancer just naturally. If they all got 10,000 milliram, then you might get 41 or you might get 40, because the probability now is 40.5%. 40.5% is the chance of these people getting cancer. That's what that means. And that's a big dose. That's a really big dose. Let's keep going up, keep going up. 100,000 milliram. That's a 5% chance of cancer. So now if you do 100,000, you take the same 100 people and you give them 100,000 milliram. This is the kind of doses that you get acute radiation syndrome from. You give them all 100,000 milliram, then 45 of them are going to, on average, going to get cancer. Now, you don't know which 5 got it from the radiation, because the other 40 were still going to get it, but an additional 5 got it from this kind of a dose. And these kinds of doses, we know this from the atomic bomb survivors. That's the kind of exposure you have to get this kind of a dose. Oh, let's keep, all right. 500,000 milligram. This is called a lethal dose. So now we're talking, this is again, atomic bomb survivors. If you get this kind of a dose, that within 30 days, half of the people that get this dose will die if they don't get medical treatment because of acute radiation syndrome. It's not cancer, it's acute radiation syndrome that's going to cause this. Basically, your immune system is going to be almost completely gone within a couple of weeks if you don't if you don't get to a hospital. And 1,000,000 millirem at this point, or 1,000 rem, you're effectively in hospice. You are being given pain medicine because you don't have an expected path forward. So let's summarize all this. That was a lot of stuff. All of the stuff that you see up on top in green, there are, if there are any effects from those kinds of doses, they're too small to see. So as a scientist, I can say with statistical certainty, if there's an effect there, it's too small to see. That's the point. Everything below that, if you get a dose like that, you can see an effect. Now, it can be really hard to see, like at 10 rem, that could be really hard to see, or 10,000 millirem, but everything in the green up there, that's where regulations are. And so as a scientist, that begs the question, how much time, fear, money, and stress is it worth to focus on something that doesn't have a measurable medical effect? That's a very profound statement. all of the stuff in green, if there's anything that's happening there, is too small to see. So how much time, money, fear, and effort is worth something that's too small to see in terms of medical effects? No scratches, no bruises, nothing that you can measure, literally. And that's where we are. And the point is that those kinds of doses can terrify people. And we'll see some very acute examples as we go. But that's radiological risk in context. So now let's come back to the fuel cycle and the parts that when it comes to radiological risk that also scare people. Use nuclear fuel. That can terrify people. And one of the most important things to remember is that even if we never made more electricity with nuclear energy ever, we still have to figure out a path forward. And so it doesn't matter whether we're going to make any more nuclear power plants, we still have to find a path forward for the used nuclear fuel. Now, what we do is we put them in these dry cask storage in some form. And once it comes out of the cooling pond in the nuclear reactor, it comes in these dry cask storage. And what's in it is what you see down in the bottom in the little hand there are the uranium dioxide pellets. That's what actually is the fuel that goes into, in the top left, the fuel rod that goes into the fuel assembly that goes into the reactor. And after it's spent and it's cooled off in the cooling pond, it'll go into these storage casks. And these storage casks they're basically passively cooled. And again, these can scare people, but these are, as we'll see here in a moment, these are virtually indestructible. You can destroy them, but they are virtually indestructible. And they're passively cooled. And wherever the fence is, wherever you see a fence, remember the dose rate at that fence has to be about a third of natural background by law, or they violated a regulation. And so the dose rates from these things are negligible in terms of any kind of a consequence, because again, the dose rate at that fence, it can terrify somebody to know that there's nuclear fuel radiating anybody that might stand at the fence. It's a fraction of natural background. Now, let's contextualize the scale of this. I love this statement from the Department of Energy. I think that it really helps to contextualize it, that for about the past 50 years, the United States has got about 20% of its electricity from nuclear energy. So the largest economy on the planet, the largest economy the world's ever known, 20% of the electricity comes from nuclear energy. That's a lot for 50 years. That's huge. And yet all of the used nuclear fuel from all of that energy would not fill up a single football field above 10 meters high. That's how small it is. It's just an easy to deal with problem, and yet it terrifies people. And again, there's that cognitive dissonance of the narratives that we hear that resonate with us, that sound like, yeah, I need to be afraid of this. So this is the testing that's required in order for you to get a license from the Nuclear Regulatory Commission to build one of these storage casks. The design has to have a 30-foot drop onto an unyielding surface. It's got to be on its weakest point, 30-foot drop onto its weakest point. Then that same cask has to do a 40-inch drop onto a steel bar. Boom! On its weakest part. So after it did the 30-foot drop, it's got to do the 40-inch drop onto its weakest point. Then it's got to go basically in a tunnel fire for a half an hour. And then it's got to be submerged under 50 foot of water for 8 hours. The idea being is that what's the worst that could possibly happen? The worst that could possibly happen for a transportation accident is that it falls off a cliff, right? That's the 30-foot drop onto onto its weakest point, onto a big boulder. But then it rolls off onto a spiky boulder. That 40-inch drop is a spiky boulder on its weakest point. And then for some reason, it's in a tunnel fire. And then as it comes out of the tunnel fire, it falls in a lake. So the same cask has to sequentially go through all of these in order for that design to get a license. And it can't leak. After each of these steps, it can't leak. And it does it sequentially. That's why I would say they're virtually indestructible. Now, you can destroy them, but they're virtually indestructible. They are extremely robust. They're huge. They're hard to move. They require very large, specialized equipment to move. And that's what's required. The context here is that the general design criteria in nuclear is that we design them so that the worst thing that could possibly happen in the worst case scenarios is that nobody gets hurt. That's our design criteria. The worst that could possibly happen is that nobody gets hurt. Imagine any other industry put to that standard, how would they perform? So I used to work here at the Waste Isolation Pilot Plant. It's a geological repository in southeast New Mexico. And it's about a mile and a half. It's about a half a mile down in a stratigraphy that has about a mile thick of water evaporites. Most of it's sodium chloride, but there's also calcium sulfate and other things. But water evaporites. Now, this is on the right, shows you the stratigraphy. You can see there in the middle, the WIPP facility, and most of the gray stuff, that's sodium chloride. There's also some calcium sulfate, basically stuff that would evaporate from ancient seabeds. This is about 200 million years old. On the left, you actually see a miner remotely operating a miner. So the mechanical miner that's mining is like this big drill, it's just drilling the salt. And it's the salt that's is basically just a nuisance dust. It just causes visibility. It's literally just sodium chloride, and that's what it is. This is considered incredibly stable geology, so that it will sit there until the waste literally just decays down into a different kind of dirt. That's the design specification. Now, while I was there, this happened. Now, on the left, you see the workers installing the drums, installing the waste in the underground. On the right, you see what happened in 2014 on Valentine's Day. One of those drums deflagrated. Los Alamos sent some really bad drums down there, and for all intents and purposes, it exploded. And the funny thing is that that trace you see there on the right, that was basically the plume. That was the validated plume. That's what I published here in this bottom left paper when I did the consequence assessment. And that looks scary, right? Big green glob. That looks like the Simpsons or something, right? But the funny thing is that if you were right there at this purple flag, this WIPP far field, that's the closest place that a member of the public could have been. If you had stood there the entire day of that release, that you would have gotten less than 10 millirem. That entire release was a fraction of the EPA license limit. The 10 millirem per year to the nearest resident would have been out here at Smith Ranch, and it was a small fraction. It was about 1%. So the release was within their license. It was a legal release based on what they were licensed to release every year. Usually they just release nothing, but this year they actually did release a little bit, but it was a small fraction of their license. Remember how small those license limits are, 10 millirem per year to the nearest resident. That was the license. The amount of americium in this that deposited on the ground was comparable to the amount of americium that was already there before they built this facility due to atmospheric nuclear weapons testing in the past century. It covered the earth with trace amounts of transuranics and fission products, and the amount that was there was comparable to what was put there from that release because the safety features work. Again, the design specification for nuclear facilities is that the worst that can possibly happen is that nobody gets hurt, and that's what happened here. And I was there. I was the first person back on site after that occurred. Now, a lot of people like to say, yeah, well, how do you know what's going to happen in a million years, in 10,000 years, in a billion years? Well, modern geology is really impressive. And there's a place in Oklo, Gabon of Africa. There was a uranium mine that was there. And that uranium mine, I did some research myself, is down here on the bottom, where if you look at natural uranium, the fissile component, uranium-235, has a shorter half-life. It's got a half-life of about 700 million years. The non-fissile component, uranium-238, it's got a really long half-life. Its half-life is about the age of the Earth. And what the half-life tells you how fast it exponentially decays. But it also tells you, if you go backwards in time, how fast it exponentially increases. So if you go back about 2 billion years, the fissile component, uranium-235, it would have been at an enrichment that's the same as commercial nuclear fuel, about 5%. And if 5%, a little bit of water gets in there and it allows it to go critical. And so you say, well, how do you know? How do you know that that happened? Well, it came down to the geochemistry, the isotopics. If you look at neodymium, it's the element that's got 90 protons in it, but it can have a number of different neutrons, meaning that it has a number of different isotopes. And that's what you see here in this top left histogram, is the distribution of isotopes that you have in neodymium. Now, if you do a weighted average of those, you can see that it goes from 142 up to 150. If you do a weighted average of those isotopes, you're going to get this number, the atomic mass of neodymium, of 144.243. So you can see that's right right around the middle of what the actual masses are of the different isotopes in neodymium. Now, why this is significant is because the neodymium that came from Oklo is what we see down here in the bottom left. It's completely different. It's an isotopic distribution that we've never seen anywhere else on the planet ever, that you don't get this. It doesn't happen naturally unless you do this. And you look at the neodymium, the distribution of isotopes you get from fission in the top right. And if you do a superposition of neodymium from fission and from natural uranium, you can basically almost identically reconstruct the neodymium from the Oklo. So that if I subtract out the natural neodymium from the neodymium found at Oklo, I basically exactly reproduce neodymium from uranium-235 fission. And so what this means is that the fission products were generated in the Earth and they stayed there for 2 billion years. So stable that literally Mother Nature made her own natural nuclear fission reactor. She made her own spent nuclear fuel and she buried it in a place where there was stable geology so that it literally just decayed back down into a different kind of dirt. And so that's the point is geology tells us how we can dispose of this, how we can remove it from the biosphere permanently until it just decays down into a different kind of dirt. And the point is geology works. Well, where do we get dose? Where do we get all these doses from? I had mentioned you get about 310 milligrams per year from natural sources, but you get more than that on average if you're an American from medical sources. On average, we get about 625 milligram from all sources combined. Now, most of that is medical, computed tomography, nuclear medicine, but the biggest part of our natural radiation dose comes from radon. Basically, every breath you've ever taken has been radioactive. It's had a little bit of radon in it. Every piece of food you've ever eaten has been radioactive. It had a little bit of potassium in it, and those are naturally occurring radioactive materials. And that's where that natural background comes from, is from the natural radioactivity, primordial radioactivity that's been on the Earth since it was formed, and it'll be here long after it's anything that looks even remotely recognizable to what it does today. Here's a distribution for the United States, and you can see that around the Colorado Plateau, that's where you get the most cosmic radiation. As you can see here in the top right, you get the most potassium on the Colorado Plateau, as seen in the top left. In the bottom left, you can see you get, again, on the Colorado Plateau, the most amount of thorium, and again, on the bottom right, the most amount of uranium. And so for the people that live up there on the Colorado Plateau, they get a much higher dose than the rest of us that live, say, on either the East Coast or the West Coast, or even in the Midwest, where you can see generally the doses are going to be a lot less. And so you can get substantially larger variations in natural background simply by going and visiting Denver or Salt Lake City, where you're going to get much higher values of these radioisotopes just from natural sources. All right, let's talk about the environmental impact because we don't want to have a large environmental impact from basically anything that we do. And why is it that renewables are so important? Why are they important for environmental impact? It's because of greenhouse gases. It's as simple as that. That's really it. After you build renewables, they don't emit greenhouse gases while they're making energy. And I'm showing that on this graph. You can see the amount of greenhouse gases from a life cycle that nuclear, it's actually better than photovoltaics. This came from a Department of Energy source. But the reason why I picked this graph is because it categorizes nuclear as non-renewable, but it categorizes geothermal as renewable. And the reason why I want to bring that up is that the majority of geothermal energy comes from the radioactive decay of the primordials, uranium, thorium, potassium. That's where most geothermal energy comes from, is the radioactive decay. Remember, I showed you that graph of how much uranium and potassium and thorium there are just in the United States. Well, it's basically everywhere. And that radioactive decay in the earth, deeper in, it gives off heat. And that heat, it can be realized in terms of geothermal. And so if I would argue if geothermal is renewable, nuclear surely is. I mean, just from runoff alone, we have about over 4.5 billion tons of uranium in the ocean right now that we could passively extract, just not cost effectively, but just and that's just from runoff of from the oceans and hydrothermal vents. So it's just being reproduced continually by plate tectonics. So, I mean, if geothermal is renewable, nuclear is even more so, but especially with the half-lives, right? The nuclear is going to last longer than the sun, particularly thorium. Well, one of the other things about nuclear is that it's high energy density. I said back at the beginning, per atom, on a per atom basis, you get about 200 million times more energy per atom from nuclear than for fossil fuels. And so you don't require a whole lot of fuel. Now, if you look at this graph right here, this came from the World Nuclear Organization. And in terms of building the facility, building the power plant, that's just it, building the power plant, coal and natural gas, they don't require a whole lot, but they require a lot of fuel and they produce greenhouse gases. Nuclear, because it doesn't require a lot of fuel, it doesn't require a lot of materials. But wind and solar, for the same amount of energy, to get the same amount of energy out, you're going to need a lot more materials. And why I bring that up for environmental friendliness is that all has to be mined, right? You're going to need mines to get the concrete, to get the steel, to get the silica, to get all of the materials. And that's going to require milling. That fuel cycle that we went through with uranium at the beginning, the others all have fuel cycles too. They just require a lot more materials. And so the environmental impact from that is substantially larger if you're going to use something besides nuclear. And then there's the amount of land that you're going to take. I've heard people say, well, you only need to cover all of France with solar panels to provide everybody with energy, right? I mean, but on that same scale, it would take something on the size of Paris with nuclear power plants if you're providing the same amount of energy. And the point is that how much land do we have to devote to energy? This is a logarithmic scale. So if you see nuclear here on the bottom left, every time I go up an increment, that's an order of magnitude, a factor of 10. So that nuclear is basically 100 times less land than solar. And that makes sense. It's, again, energy density. And how much land do you want to devote to energy? As little as possible. All right. Now let's talk about nuclear accidents. I told you we would. Now is the time. 3 Mile Island. For many people, that statement is a terror statement. That statement is a reason why we shouldn't do nuclear energy. And that incident is why I started the radiological risk at 1 millirem. 1 millirem, if you look at the radiological dose to the average member of the public, it was a millirem. And that to them was terrifying. What you get in one day, they got from the entire event on average. And it's still terrifying because you don't know. I mean, remember when we started, I said, what's 10 to the minus 5 joules per kilogram? I would not even be surprised if Chris didn't even know what that was, because I intentionally picked a very obscure unit. And so it can sound like, who knows what that is? I don't know. How do I convert that? I need to look up what those conversion coefficients are. And so 1 millirem is just the same gobbledygook to most members of the public. They don't know. All right, let's talk about something a little more scary. Fukushima. Fukushima, if you look at the United Nations report, the World Health Organization, any of the review papers, what they'll tell you is that the only deaths to any member of the public, the only public deaths from Fukushima were from the panicked evacuation. Remember that evacuation criteria at 1,000 millirem or 1 rem? That's more than what members of the public got. And yet you got to get all the way up to 10,000. Nobody got even close because they evacuated before that. And yet that terrified people, right? About the dose that you get for a nuclear medicine scan, that's about what they got, or a CT to the head or hip or something like that. I remember when I was a boy, I had to get a CT scan to the head. The point is that terrifies people because you're going to say, how can you tell me it's not a scary dose if you're telling me I have to move from my house permanently? That's terrifying. If it's not a big deal, if it's like a nuclear medicine scan, why are you making me move? That doesn't make sense to me. I don't trust you. I think nuclear is bad and scary. And that's where we are. That's where we are, is that the radiological consequences are not understood by people. We do that conservatively. Remember, the criteria is that nobody can get hurt. And we failed there, at least the Japanese did, because the evacuation killed a few thousand people. And then that was to avoid a dose that would have had no measurable medical effects. All right, let's scale it up. The one that people like to use a lot to say why we should not have nuclear energy is Chernobyl. Now, Chernobyl, yes, it was a bad design, it was a bad operation, and then no emergency response. Basically, if you'd have done any one of those three right, you could have largely just removed all of the medical effects. If you'd have done any one of those, just pick one, and a lot of other things you could have done to have prevented it as well. But the point is it would have been easy to have stopped that if you'd have just decided you were going to do it right. Any of them, built it right, have a containment, don't operate it in these extreme conditions intentionally, do emergency response, just things that seem to make sense. And so there was something on the order of about 4,000 cancers. Now, most of those are treatable, but still, you caused a statistically significant increase in public cancer there to the people in that area. Now, the reason why I specifically cite this paper here in the bottom right is that this is going to shock you. It turns out that they did a study of Estonian liquidators, the people that went and cleaned up Chernobyl, shoveled the graphite. If you've seen the Chernobyl miniseries, it's those people that were cleaning up, those cleanup workers. Now, when the Soviet Union was in place, Estonia was part of it. And so they went and they said, all right, let's go look at the men from Estonia that were not in the military at the time. So they didn't go to Fukushima, or sorry, to Chernobyl. And let's compare their health outcomes to the men of Estonia that did go to Chernobyl. And in this paper that was published not too long ago, they showed that there was a small, statistically significant increase in cancer. That yes, they did have an increase in cancer. What was shocking was that even though there was a small increase in cancer probability, there was a massive increase in suicides. And the point was is that again they didn't know, right? Chernobyl radiation is like magic. Is like if you have arthritis, do you know that? Can you say that Chernobyl didn't cause that or contribute to that? If you have a balding, if you have hearing problems, if you have any natural condition that would occur anywhere otherwise, how can you not blame it on Chernobyl? Because you don't know. You know, Chernobyl, who knows what radiation does? How many people know, what radiation does to somebody? Most don't. It just causes cancer, it causes disease, and Chernobyl is even worse. And so whenever something bad would happen to them, medical wise, or they'd have a health effect, they'd get a cold, it must have been Chernobyl. And so anytime something came about that was a deleterious health effect, it just confirmed, it was a self-fulfilling prophecy that confirmed they have no hope, because it was proof that Chernobyl was just going to keep getting them sick. And so the suicide rates just spiked. And why that was so crazy is that means more people were dying from fear of radiation than from the actual radiogenic effects. That's what's crazy. Just like with Fukushima, more people died. The only people that died were from fear. That's just crazy. That's just how extreme these narratives are. Like I showed you, right? Remember those regulatory limits. Your water limit is the same limit that you get for a flight, coast to coast flight, New York and back, New York to LA and back. That's going to scare people if they know that they had too much radioactivity in the water by 10%, right? That could make headlines. Now, a lot of people also like to point out terrorism, right? What's going on with Zaporizhzhia? They think that's a reason not to do nuclear energy because it's a terrorist event. Even before 9/11, these things were designed to withstand head-on impact of a large jetliner. So the design of our containments would receive a large jetliner doing a 9/11 right into it with no release. That was the design, and we've improved it substantially after that. But the me as a health physicist, I would much rather have somebody be bombing a nuclear power plant where it's not going to hurt anybody than a city where you have people. The same with those casks. Those, I said they're virtually indestructible. I'd rather see one of those rolling down the road from a terrorist trying to blow it up than the terrorist actually blowing up a bus with people in it, right? Because one just scares people, one you actually kill people. So if you look at the total number of deaths per gigawatt hour from the different energy sources, if you fold Chernobyl in, and a lot of people do that, you can see that here in this report from the UNSCEAR. Even with Chernobyl folded in, nuclear is safer than wind. It's about as safe as solar. That's with Chernobyl folded in. Now, some studies say it doesn't make sense to fold Chernobyl in. That's like folding in the Hindenburg with modern air travel. That just was a bad design. Everything was bad about it. We don't do that anymore. And so you don't fold it in. And then what happens is you see down here on the bottom right, if you take Chernobyl out, nuclear is far safer by well over an order of magnitude, safer than solar, simply because you get so much energy for so little effort. And so you don't have to do so much mining and milling and any of those other things. Uh, and with that, I want to say that we at NC State actually teach this online. I administer our online graduate certificate in health physics. That's radiological risk, radiation safety. That's what I do. That's what I teach. That's what I do research in. And we have this as an online graduate certificate. It was originally part of our online Masters of Nuclear Engineering degree that, as far as I remember, it's been ranked #1 for an online Master of Nuclear Engineering. It's been ranked #1 for as long as I remember. And this was part of it. But now I've got something really amazing to tell you. COVID taught us a lot of lessons at NC State. It taught us that we can actually do research online under special cases. And so we've actually rolled out an online PhD. It's identical to the program we have on site. There are no changes. They're all verbatim. Exactly the same requirements have to be met. the caveat is that you probably need to be working at a national laboratory or something like that in order to do your research remotely, or you're doing analytical research or something like that. But because we have this online capability that we had with our Masters of Nuclear Engineering and our graduate certificates, now we offer that in a PhD. You can get an online PhD. I actually have a PhD student up at Los Alamos who's doing her research in crit safety. So I just wanted to point that out. If you really like this subject and you want to dive in academically and earn an academic credential, this is an option that you can do at NC State. So with that, I'm ready for questions.
All right, let's thank our speaker. So we have 6 questions in the chat here. So the first one, so we have questions that I will get to about the linear no threshold approximation and then also radiation hormesis. Yes, but I do want to also there's some questions about when you showed those doses, the log scale doses, uh, are those acute all at once or are they distributed throughout time, and does that make a difference?
Oh, that's a great question. Yes, it does make a difference. So these consequences that you see down here, these are for these would be for a protracted exposure. If you have an acute exposure, and I didn't point, I just didn't get into that, but it's a great question. Like a CT scan is an acute exposure, and that's where this data comes in, where children that have had radiotherapy, if they actually do have a small increase of reoccurrence. What ends up happening in the medical field is that if you can kill cancer without cutting somebody, that's a huge deal. It's a huge risk mitigation, because if you cut them, there's risks with that, and sometimes you'll have to do that. But if you can do it with chemo and with radiotherapy, then you don't have to have surgery and you don't have to have the hospital stay. And so if you did have a reoccurrence of cancer, then you could just treat it again. You'd be monitoring the person and you could just treat it again, but you've given them, anywhere from 5 to 20 more years. And again, it's only a small increase in reoccurrence compared to the natural occurrence that you already have. So acute exposures do have a higher risk coefficient than protracted exposures. Basically, the body's able to reproduce, to repair itself. And so that is something. I didn't go into that. There are other things that you have to look at, like the chemical form of the radioactivity, the type of radioactivity that you have, and how it gets into the body. All of those would affect the dose. That again would be in the degree program if you wanted to look at those the dose coefficients from different types of exposures and how that contributes to effective dose. Then that would be where we dig into that here if you wanted to get uh, accredited or the graduate certificate in health physics.
All right, thank you. I think I'll combine these next 2 questions. So one is from, I apologize in advance if I'm mispronouncing any names, but from Marcel Lacroix and then from David Erickson. So the first one is, if there are no measurable health effects for doses smaller than 1 rem, so why is the linear no threshold model still used in nuclear regulations? And then the other question, oh, sorry, it's actually the other question is from an anonymous attendee. But that is adding to that, what are your thoughts on the studies that show that a small dose can be beneficial to your health? You seem to be presenting a linear no threshold model. Is that best for public communication or some approach to talk about the scientific debate on the limitations of the model?
And so I'm going to answer those as 2 different questions. Why is it that in design we use linear no threshold? And then I'll answer the technical basis around linear no threshold. So the reason why we use it is because it's a good metric. And here's why I would say it's a good metric. We have in our industry something called a LARA, as low as reasonably achievable. And the philosophy there, if you look at the regulation, a lot of people abuse it, and I don't think they really understand it very well. The philosophy behind a LARA is that you treat dose as like a waste term. As a good engineer, you should design your product so that you minimize your waste. I mean, you're never going to get zero waste, but you want to minimize your waste. You don't want to have a lot of waste. You want to minimize your waste. And dose is a waste term. It's something that you can be a LARA and you can increase the doses to your people by a factor of 10 and still be a LARA. if you increased your productivity by a factor of 20, because the product per waste went up, or the waste went down or product went up. So that ratio is the metric that you use for a LAR, and you treat the dose as a waste term. You want to be able to show that you can control radioactivity, and that's really all that a LAR does, is it shows that we can control anything that provides a potential vector of exposure of dose to people, whether it's surface contamination, whether it's airborne, whether it's ambient dose rate levels, any of those kinds of things. It's just maintaining positive control. It's effectively a quality control program, a quality assurance program. You just trend it to make sure that you are controlling ionizing radiation fields, and that you're optimizing productivity at the same time that you're minimizing all of your waste. And dose is just one of the many waste terms. So that's why LNT makes sense from a regulatory perspective, from a design perspective. And I've actually got an article in the Health Physics that I journal where I talked about that. That's my opinion. And I used to do ALARA. I was the ALARA coordinator at WIPP, and I teach ALARA. Now let's talk about the technical basis for linear no threshold. So that's a different thing. So the way that you implement it for regulation and for control is not the same thing as the technical basis. The technical basis is that in this top left here would be this is simulated data. This came from I forgot his first last name, Boyce, John Boyce. He sent me this paper, and it's a great paper. But the point is that if you look at the data, this is just a simulated data. If you look at the data, you only see data that's well up into around around 10 or 20 rem, where it looks quite linear. Now, whoops. For example, that or that 10 rem, that's about 0.1 gray. So if you look at this data here on the far right, I don't know if you can see my cursor. Can you see my cursor? Hopefully, I don't know if you can see my
Yes,
cursor.
I can. Yep.
Okay. So you see this data right in there. There is no statistically significant difference there. If you come down here where they truncated the data, you can see it looks like it would have went negative, but that's around that same dose level. Again, right here where you can see that they did not truncate the data. You can see, yeah, it looks like it maybe went negative, but who knows, right? The uncertainties are huge. If you go here to the far left, right? What is this right in here? Some of them are negative, or some of them are less than one, meaning a health effect. Some of them are more than one. The point is there's no statistically significant difference. If there's an effect, it's too small to see. Now, the technical basis says, who knows what's going on here? We don't know. Now, there are a lot of publications for a lot of theories. Now, this hormesis theory, this is the one that you see here where it's like medicine. A little bit is good for you, but a lot is bad, right? You don't want to overdose on anything. You want to take a healthy dose. You don't want to overdose. And the theory behind that is that that life evolved. Oh, the first cell came around maybe 3 billion years ago, something like that. And just like the natural enrichment of uranium was basically, commercial nuclear fuel or better, you had exponentially increasing radioactivity. So life evolved in a much higher environment. So life would have been designed to be able to mitigate much higher radiation fields than we have today. And so if we're designed for higher radiation fields, that would be consistent, that would be consistent, and where's my cursor? There it is. That would be consistent with the hormesis effect, is that's what we're designed for. Back what the biosphere was, back when evolution was happening, that's what that was. Now, there's another model here that you can see, another popular one. This is the threshold model. The threshold model is, it says that, well, when it comes to radiation, the body basically repairs it. And the body's repairing all kinds of things to the DNA. The DNA is getting all kinds of defects, and it's being repaired continually. And it's like heat. Within a certain range, our body can compensate. Or vibration. Within a certain range, our body can compensate. So that, at too much vibration, we'll break apart. At too much heat, we'll die. But within a range, our body can compensate for that. And that's what this hormesis, or that's what this threshold model is that the body can simply repair the DNA, and it has effectively no effect all the way up to some threshold. So that's what the threshold model is. And then you can have like a sublinear or the superlinear, but the linear no threshold is simply, it's the simplest model. That's really all that it is. Now, there's a lot of theory that argues that you could have something else like this, but the simplest model is just a line, because if you look at these other curves over here, there's no statistically significant difference between these models. And this is the best data that we have. And we've been studying this for a very long time and spending a lot of money looking at it quite in detail. And so I'll end with, I just got a paper accepted for publication in the Health Physics Journal. I'll be presenting on this paper at the ANS summer meeting, a little pitch for my presentation, in the Radiation Protection Shielding Division's general session, where I was able to show that if you go back to the literature and you look at the placebo effect, the placebo effect is effectively if you give somebody if somebody's in pain and you give them a sugar pill and you say this is pain medicine, they'll their stress levels should go down. They'll attribute that to the sugar pill, and that will make them think that the pain is being addressed by the sugar pill and they feel better. Now there's an opposite thing. It's called a nocebo. The nocebo effect is if I give you a sugar pill and I tell you it's poison, you're going to stress and you're going to attribute you have a possibility of attributing that stress to the poison, the sugar pill. And so you're going to think that you're sick because you're stressed and it's a sugar pill. Now it doesn't work on everybody, but around 30% of the people actually have a noticeable effect from placebos and nocebos. And why I bring that up is that if you look at the research that I did, I show that fear of radiation is a nocebo. Remember, I told you about Chernobyl. People were committing suicide in the droves. How stressful is that? And what the regular medical literature shows is that if you have if you live in continual stress or fear or depression, if you have continual high stress, high depression, high fear, your cancer probability just simply goes up. You have a much higher probability of cancer because you have a really stressful life. Stress is literally that unhealthy. And I point out in the paper the medical path that takes. But the point is your cortisol levels, that's fight or flight. You're supposed to be burning that. And if you're not burning that, your body's processing it and it's not healthy. And your probability of cancer goes up. And so the only times, and I've showed this, the only times where there have been claims of like a superlinear effect, where people are getting low doses that are well below these like thresholds that you would have with the other models, getting doses well below that, and they're claiming cancer, it only occurs if you knew about the effect beforehand. If you look at cases where people got doses higher than that and they had no increase in cancer, it's where they did not know about the radiation. So if you don't know about low doses of radiation, it's no effect or potentially even beneficial. If you do know about the radiation, like you're getting radiotherapy and you're afraid of it, then you do have then there are journal papers where show that you have an increased cancer rate. So that fear of radiation is effectively a nocebo.
That's very, very fascinating. We have maybe time for one more question very quickly, and we do have one from an anonymous attendee that is along the lines of what you were just saying. And that question is, airlines never give talks about safety, even given recent accidents. By preaching
Mm.
safety, are we making people think that nuclear is unsafe?
In a sense, yes. For example, like when I showed that graph that if you exclude Chernobyl, the deaths per gigawatt hour are orders of magnitude lower than solar, and you could say, well, that makes it a lot safer. But they're both basically right near zero, right? To die from solar, you got to fall off of a roof or get electrocuted or something like that. For accidents for solar, there's just not a lot of those. They're not zero, and if you exclude Chernobyl, they're higher than with nuclear. But if you say something like that, then again, a person's not necessarily going to think in logarithmic scales, right? That's kind of abstract. And that's the way that you're arguing if you're saying that nuclear is that much safer than solar if you exclude Chernobyl. Another example would be the way that we like when we do nuclear waste disposal, right? I showed you that model of WIPP where you dig something a half a mile down, and then we say this is really safe. And you say, well, if it's so safe, why do you got to dig it down a half a mile? Why don't you stick it in your backyard if it's that safe? And it's like, well, I could, but that would terrify my neighbors.
Well, we're just about wrapping up on time, so I think I will thank you all for attending this evening's webinar, and thank you to Dr. Hayes for speaking. ANS will be hosting these webinars monthly. You can learn more about them and about the ANS STEM outreach efforts at ans.org/nuclear. Additionally, if you would like to stay in the loop regarding other ANS nuclear education programs and events, you can sign up through our link in the chat, which Chen is dropping right now. Oh, hopefully that came through.
Can we do the other survey?
Oh, I think it is. I think that is it. So I think everything automatically ends at 5.
Oh, okay.
Survey. Yeah. Well, yeah, I think that's it. So yeah, thanks again, Rob. I thought that went really well. I think it's really important to put these things in perspective. So
Thanks for having me. It was good.
yeah, thanks, Jenna. Thanks, Janet. I guess I hope you all have a good night. I'll talk with you all later.
Thank you.